Chapter 18 is about move semantics. And what is move semantics? Well, to talk about move semantics, we have to first go to talking about this concept of value categories of expressions. So every expression in C++ language has two properties. One is type, the other one is value category. So for example, 1 plus 2, that expression, it has a type of int, but then it also has a value category. What is a value category? So value category essentially is it's basically a categorization of an expression so that the compiler can determine what to do with it. And like, for example, when it comes to so when it comes to whether your expression can be put on the left-hand side of the assignment or right-hand side of the assignment, and that is one thing. So it depends on the expression. If you're not using this properly, the compiler is going to complain about it. And so this little diagram here actually shows you the different types of value categories that's available in the language. And so there are actually two, an expression can be either a GL value or R value. Okay, now this seems a little weird. What is a GL value? GL value stands for generalized L value. And then what is L value? L value is, for historical reasons, it's called L value because before the newer version of the standard came along, the way to differentiate different value category was simply say if the value can be put on the left-hand side of the assignment or the right-hand side. So the left-hand side expression is called L value, and the right-hand side of the expression is called R value. Now, that name stuck, but it doesn't necessarily mean it's a very accurate definition. It's not accurate definition anymore, but still gives you an idea what L value and R values are. And so a GL value simply is either a L value or X value. And what is X value? X value stands for expiring value. There are only a few types of X value. For example, if you there's a casting to a certain type. Anyway, so I don't want to get into the details. Actually, you can actually look up these value categories in the reference website, and you actually, there's a lot more discussion there. Now, there's also, I just kind of just go over this real quick, and then we're going to actually focus on L value and R values. Now, R value could be either X value or PR value. PR value stands for pure R value. Like 1 plus 2, I just mentioned, that's a PR value. Okay, so there's one way to look at this, and that's what the textbook actually talks about. As far as to be able to use the move semantics properly, you actually just need to understand whether the expression is L value or R value. Now, so basically an expression can be either L value or R value that covers all of the different value categories, okay? So with each value category, there's actually different properties or rules associated with them. Let's take a look at the L value expressions more closely. So an L value expression evaluates to some persistent value with an address in which you can store something on an ongoing basis. So the keywords here are an L value expression has a permanent location. While the permanent location is kind of relative. It's obviously abides by the scope of the variables involved. But otherwise, the value, the result, the evaluated result of that expression is put into a sort of a place in memory that has an address. And this address you can actually retrieve, and you can store values into that. So what are some examples? For example, obviously the name of variable, that is an L value expression. The name of a function as well. And another example would be a function call. Okay, a function call if the return type though is an L value reference. Now, what is L value reference? Well, basically all the reference types that you've seen so far, they're all L value references, because the way to declare an L value reference is use this ampersand symbol here for, right after a type. And that T ampersand, that is an L value reference. So now we used to just say reference. Now we are trying to be specific. That's actually called L value reference. And another example would be the indirection expression. So let's say you have a pointer P and you basically use the indirection operator, and then you get and the result of this essentially is the address, that becomes the object that this pointer points to. But this expression can be put on for example, on the left-hand side of an assignment, because this is a L value. It has a location you can retrieve, obviously, as a pointer. So the properties of L value expressions are the address of an L value may be taken by built-in address of operator, right? For example, this indirection expression, you can use the, obviously get the address of that goes back to the pointer value, right? It's kind of negates that indirection operator. So, and then, if you have a name of variable, then you obviously can retrieve the address of that variable. And a modifiable L value, basically non-const L value, it may be used as the left-hand side operand of the built-in assignment. That's kind of what we've been talking about. That's kind of the origin of the name L value. And, obviously a modifiable L value can be put on the left-hand side of the built-in assignment or compound assignment operators. An L value may be used to initialize an L value reference. So yeah, so basically that is kind of a no-brainer, right? So you can initialize it. You want to make a new reference, an L value reference, T ampersand, a reference to T. And then you can make such a variable from a L value expression. For example, the simplest one would be the name of another variable. So this establishes an alias to the other variable. That's an L value reference. Now, what about all value expressions? An all value expression, the value is to a value that is stored only transiently. So it's a temporary object. Okay, that's kind of the hallmark of all values. An example, for example, like a literal. A literal would be an all value expression. Well, except the string literals. String literals actually are L value expressions. A function call, if the return type is not a reference. Okay, if the return type is not a reference, that function call is an all value expression. There's actually a lot more of, obviously. I'm just kind of showing you some of the most common all value expressions that you see. And with all value expressions, the address of an all value cannot be taken by built-in address of operator. Okay, this is in contrast to L value expression where you can get the address of that object that's the result of the expression. But if you have an R value, the end result, it's stored somewhere as a temporary object, but you cannot retrieve the address of that. It's just not allowed. So an R value cannot be used as the left-hand side of an assignment or a compound assignment. Right, this is kind of a major difference between L value and R value, right? Of course, you can put it on the right-hand side. Now, R value may be used to initialize a const L value reference. So we've been using that quite a bit also, right? So, you just have not realized what is R value. Yeah, so you can actually use R value to initialize a const L value reference, okay? It has to be a const reference. Now, that is important because if it were not const, that means you can modify the content of that R value. That would not be, that kind of defeats the purpose of that temporary object that in a location you cannot access. So yeah, you can initialize a const L value reference. So how do you actually declare R value reference? You use this syntax, which is double ampersand. Don't, that's just kind of the way to declare such a type. That, don't read too much into what this, double ampersand actually does, but this is just is designated the way to make an all value reference type. And so here's a simple example of all value references in a little program. So let's say you have a int count and this variable. So you basically define this variable with a value of 5. And then next thing is we're going to make actually an all value reference called rtemp, and which is initialized as the count plus 3. The count plus 3 this expression, by the way, is an all value expression. All the arithmetic operator expressions, those are actually all value expressions. And so, yeah, you can use all value to initialize a value variable, right? So if it were not all value, for example, it will not be able to use a L value to initialize an R value reference. It's just not allowed. However, you can easily turn a L value reference, well, L value into R value. So there's an easy way to convert that. So of course, the very last line is an example of L value reference. Then that you initialize the L value reference with actually a L value expression here. The count, this variable name, is a L value reference, L value expression. So of course you can use the L value expression to initialize a L value reference, okay? But you will not be able to, so as we just kind of explained, you will not be able to, let's say, use this count to initialize a R value reference. Well, okay. So actually, I was trying to say, if this is a L value reference here, you cannot use a R value to initialize it because this is a non-const L value reference. If you change this to const L value reference, and then you can use the R value expression to initialize a const L value reference, right? So just kind of keep those rules in mind. Now, although you're not going to see in the middle of the program, you're going to use a R value reference like this. This is not common at all. And the most common places you're going to see R value references are going to be function parameters. And with that little basic covered, now we know the value categories of expressions. Now we're going to talk about move members. Now we're talking about these two things. So an example, well, say we have a class array, and these two declarations, there are two member functions of array. The top one is it's called a move constructor. Now it looks very similar to the copy constructor, right? Yeah, it looks very similar. Now in the copy constructor, you have a const L value reference there. And then in the move constructor, you have a R value reference as the parameter. Now, as we know, the R value reference here, it can only take R values, R value expressions can be usually initialized and passed into this parameter. And similarly to the copy constructor, there's also a move assignment operator. And so the only difference here is the parameter. Here we have a R value reference instead of a const L value reference in the case of a copy assignment operator. And so now you wonder, okay, so here's the thing, with these two members of a class, typically you want to declare them as no except. And this is just the right way to do it. And the book actually explains in a lot of details why that is. I'll also mention that towards the end. Now you wonder, what is a move? What does actually move mean? The meaning of a move, essentially, it may not be what you initially thought. Just that word move kind of means a lot of things. So specifically in C++, the move semantics, then we're talking about move. Move semantics means the meaning of a move. It actually means the ownership of a class objects of data members, basically the member variables. It's transferred to another object, usually via a shallow copy. Well, the key thing here is actually it's a shallow copy. That kind of already alludes to why move is useful. Because if you're going to do copy, the copy constructor and the copy assignment operators, when you do need to make a copy, you need to make a deep copy, meaning the objects pointed to by your member pointers, they also should be copied as well. So that can be expensive, depends on the class in question, of course. Now, the move semantics means that you only do shallow copy. Well, fundamental types, those member variables will be just simply copied because that cost is, there's no more efficient way of a copying. That's kind of with the fundamental type. That's it, right? So, but otherwise, when you have especially pointers or references, and in the case of a move, you only copy the pointers. So that's a shallow copy. And well, we know that can be dangerous, right? Like, okay, now who's responsible for reclaiming that dynamic memory? And there can be all kinds of trouble, right? So the idea with a move, then that's the reason it's called a move, is that ownership. Really, the ownership is is typically understood as if you have a class that has a pointer member variable, and this class is responsible for maintaining the life cycle of that member variable, that object that's pointed to. And in that case, when you have an object of this class, that object is set to own that resource, the underlying object pointed to by the member. That's one ownership situation. Then you also have an ownership situation where a class you hold on to a, let's say a resource that's not just a memory. Let's say maybe it's a file handle. Let's say you could be a socket, right? Various different kinds of resources that are limited resources in the system. And then that's kind of the concept of ownership. Now, a very familiar example would be the unique pointer, how the unique pointer is designed, right? From the standard library. So a unique pointer is that a unique pointer object is the single owner of the object the pointer points to. So, and in fact, this whole move semantics, and it's all obviously is in the implementation of a unique pointer, and then you see that as actually a good example of this move semantics in action. And so I want to, mention the meaning of move. That's kind of important to understand. And it's not really about moving sort of the objects around. This is about moving the ownership. So you're going to actually do a shallow copy. There's some kind of a copy, but the underlying objects pointed to by a pointer, for example, that's not, that's actually not copied, right? So why move? Kind of already talk about the shallow copy versus the full deep copy. So that means it's more efficient. It's has a better performance than the copy. So in the case where the move is a better choice than the copy. And also, of course, to provide single ownership semantics like the unique pointer. So these are kind of the two, I would say, the two most common reasons why you want to do a move. And to write code taking advantage of this move semantics, there's a very common utility from the standard library that you're going to use is this move function. Now, what does the move function do? The move function is used to indicate, that an object may be moved from. That's what it does. Actually, it simply comes down to a casting. It doesn't really do the move action itself, by the way. So that's kind of just the same. We'll make it a move ready. That's really what this is about. Maybe this function should be renamed to go to move ready. So anyway, so it can be confusing. And so this function actually allows the efficient transfer of resources from this object to another. This is kind of the definition of the move semantic, we just talk about what is a move. So this is a simplified implementation of that move function. So the standard library has a little bit more sophisticated implementation because here, as you see this comment, we're simply assuming this type T, this template parameter T is not a reference. Okay, so what if it is a reference? That there are ways to deal with that. So they essentially uses some kind of a utility to remove that reference, and so that you can make your target type to be a all value reference, right? So it's simply just doing a static cast of the argument that you pass into a all value reference. So it's turning a L value reference to an all value reference. That's all it does. Now, so we talk about this, this move utility and a move semantic. Now, where are we going to use this move semantics? So one example here you see is, it comes down to the question we have to answer. Do we want to pass by all value reference or pass by value? So since I just mentioned that, well, seems like all value reference could enable more efficient copy semantics. It's still a copy. It's just a shallow copy, right? Really, that comes down to the shallow copy. So let's see, in this example, right, we'll have this array class, and let's say we have this pushback function, much like a vector. So essentially to add element to the end of the array. Now we know the array is is a fixed size array. So we need to reallocate a new array. And now with the size that's just basically a little larger than the original size, essentially just original size plus one. Now we're adding one new element. So as part of this implementation, if we're going to take a all value reference as the parameter, and this element passed in this way, and then we want to use this move function to make it a move ready. And then you do this assignment here. So what this means is you are telling the compiler to actually use the move assignment operator. So this assignment, now keep in mind that this is, and So by the way, if you see this expression, this new array, index m underscore size, this on the left-hand side, this is obviously an L value expression, right? It has an address you can access. And in fact, this is what we're trying to do now. We're changing the value. And so with this move function, we're making this element move ready, essentially doing a casting into all value reference type. Since it's all value reference type, because if this element, this type T supports the move semantics, when we say the type T supports move semantics, means that it has the move members, the move constructor, and the move assignment operator function, okay? And that is the assumption here. If that is supports the move semantics, this is going to obviously use that the move assignment operator, okay? That's overloaded. Now, if that T also supports the copy assignment operator, the compiler is still going to choose the move assignment operator because we would change this to an all value reference. So the parameter we're passing into it is all value reference. That will be preferred. The compiler is going to pick that. And now, what if T doesn't support move semantics? It doesn't have the move constructor or the move assignment operator. Then this will degrade into the copy assignment operator here. That will be invoked instead. So remember, we just said previously, this all value reference here can be used to initialize a const L value reference, right? And the const L value reference is the parameter to that copy assignment operator function, okay? So it will fall back to copy if it doesn't support move. So that's typically kind of how you might do it when you implement a function that takes a all value reference argument parameter. Well, you may have a version of a pushback that takes the L value or basically a const L value reference, and then you have another one that takes a all value reference, right? Then you take care of both situations, right? And so if somebody calls the pushback with a all value expression, and it's going to invoke this pushback function, right? So that seems to be okay. So you kind of then you can do that. That's basically one way to do it. Now another way to do it though, we can actually go back to push pass by value. And you wonder, okay, why pass by value? Isn't that kind of defeats the purpose that is going to do a copy? Well, the thing is this, right? So if you go back to take a look at this all value reference, this function here, and yeah, you passed in a all value reference here. Now inside of it, we actually have to make a essentially we still have to make a copy of it. Now, well, never mind. What I'm trying to say is when that all value expression, when you pass that object into this function, when you invoke it, you will have a copy of that object, right? And that object and then will be moved into this new array, which will be, and then we'll do a swap so that we can change this the state of the array object we're trying to modify. Now, if you go back to pass by value, essentially you're letting the compiler to basically handle the copy right here. So essentially what is going to happen if this element it could be a copied L value. If it were an L value, then you pass that into pushback, you invoke this function with pushback. If it was an L value, then that will be copied, right? Because this essentially is object type. Now, if it were an R value, you use the R value to invoke pushback here. And then that R value will be moved into this object. That is essentially a, you basically using the R value to invoke this pushback. And if this is taking a object, and then that will actually be moved. If the compiler will just do that. This is sort of like a little optimization there. And then in that case, though, it will be essentially invoking that move constructor. If T supports the move constructor, the move semantics, if you are actually invoking pushback with the R value, that will use the move constructor to make that element argument. And then that's what you're going to use internally later on. And essentially, once you get inside this place where you're actually doing another move here, so this will be moved again, okay, which is obviously lightweight. This is still fine. So you're not really copying twice. There's always just one copy here, okay? All right. So this seems to be a viable way. Now, a viable way in the sense that if you actually indeed need to have a copy, then this is okay. The pass by value, and then what this will allow you to do is you don't need a two version of this pushback. You don't need the L value reference. You don't need the R value reference. You just have this one thing. That is a situation you want to use this if you only. So we're going to actually summarize that rule a little bit. So function parameter guidelines. So when you use pass by value, you want to use pass by value if it were you're passing fundamental types and pointers. So if your parameters are fundamental types or pointers, you always use pass by value. And if the objects of a type that of the parameter are expensive to copy, then you want to use a reference to const. And for example, the string objects that we have talked about before. And you also want to use a pass by value, as we just kind of explained, if the function inherently copies its T argument, and also T supports the move semantics. Now, if T doesn't support the move semantics, then that's not good. Then you may be copying multiple times. You don't want to use pass by value. In that case, go back to, basically the const L value reference version instead. Now, if it does support a move semantics, but then also your function always needs a copy of that argument, then you just pass by value. You kind of use one stone to kill two birds. And when it comes to returning from a function, we always want to return by value. Well, we're actually going to take another look at this. Why is that the case though? And it turns out, so here, for example, this array class, it's kind of remember the array class actually has a pointer, and that pointer holds on, points to the very first element of the whole array, right? And all the elements are on the free store. And so this array here, and then you see, okay, we're gonna make we're trying to build a string array. So we have a loop here, and actually we're gonna fill up multiple elements up to the size that's passed in, and each element is a string. And so this seems like a heavy duty array, right? There's a lot of data in it. Then in the end, we're going to return that object. And then you wonder, well, since we just returned this object, it's not a, now wonder maybe this is gonna, how is it gonna construct that return type, right? So is it gonna make a copy? Actually, it will not make a copy. So there are actually multiple reasons. Now, this is kind of the specification makes the compiler do that, right? So this is kind of the standard. So first of all, and this result is a local automatic variable. And we're returning that local automatic variable. In this case, this result will be treated as a R value. Now, what does that mean though? That means that if you invoke this function and then you want to use the result somewhere else, right? And that return value from this function call is going to be treated as an R value. Okay. So that's one. Now, if it's an R value, now suppose we'll have other rules I want to explain, but just look at this as is. If this is treated as an R value, the return value of this function call, build string array, is treated as an R value. Now, what does this allow you to do? So the place where you're going to use the return value, if if that supports move semantics, right? Then you can actually move that value efficiently to somewhere else. Okay, perhaps let's just say you are trying to define another variable. Let's say you define another variable with the result of this. Then in this case, it would have just used the move constructor to make that object, right? So, but that's not all. That is actually kind of the worst case scenario. Even the worst case scenario is not too bad. If your type supports move semantics, which in modern C++ in your program, you should always do that. So either you get the default move constructors. We're going to talk about that because they will be generated in some cases. And or if you provide your own version because it needs special handling. So either way, move semantics should be there in most of your classes you're going to write. But there's other optimization also. It's called a copy elision. Now, what's a copy elision? Copy elision means it omits, the compiler is going to omit the copy or move constructors. Okay, you wonder why. Okay, so this is interesting. In fact, it's going to do a zero copy pass by value semantics. So there's going to be no copy or no move. How is that going to be achieved? There's actually two forms of a copy elision. In this case here, we're actually returning a local named variable here, result. So this form of copy elision is called NRVO, or named return value optimization. So this result what's happening here is when you actually see this, now you're making a local variable result right here, right? This is supposed to be in this function call for build string array. And so, remember that call stack. So what's going to happen actually, this result, it will not be it will not be allocated in the space for this function call. Instead, the result object, when you define right here, because the compiler knows this is what you're going to return, this object will be constructed directly into the place where it would be copied or moved to if we were not for the optimization. But in reality, this is going to be totally avoided because this will be allocated, the object will be put directly into the place where this return value will reside. Okay, so that's kind of why in this case, there's no copy, there's no move either. So it's, there's no cost, it's got zero cost. So that's why you don't need to worry about this. Now, what if you return some kind of an expression that's actually is not a simple local variable? Let's say you return like 1 + 2, for example, some kind of R value, right? If you do return that, and you will not get the NRVO because then this will have so-called a temporary variable, the temporary object, sorry. So temporary object that normally you would think there's a temporary object because the R value, you kind of have a temporary object somewhere, right? 1 + 2, you need to, there's a temporary place to store that 3. And actually that temporary object creation will be omitted too. So essentially it will be using that the result of that unnamed temporary, it will not even materialize. It will essentially going to be just it's going to use that directly to initialize whatever, the caller site, wherever this function call is made. So that is called a return value optimization. In the case of a temporary, that construction is also omitted. Yeah, so that's why it's also efficient. You don't have to worry too much about this. And just parallel to what we talk about, the copy and swap idiom, there's also a move and swap idiom. So essentially to implement, like, for example, the move assignment operator function, same thing as the copy. So then in this case, you're not doing the copy, you're doing the move instead. So we'll actually take a look at an example shortly, but for right now, let's just take a look at the move swap idiom, not in the context of the move assignment operator, but in another function where you may use this idiom as well. Let's say you're adding this element. This is the pushback function we just saw earlier. And what we need to do is first allocate a new array with a size +1, right? Now we're adding one new element and towards the end. So you got to have a new larger array. And then you're going to copy the existing elements. And then you copy you move or copy, right? In this case, actually, you'll see this function we're using, and we're going to define this shortly. It says a move assign if no except. What does this mean? It means that if T class has a move assignment operator function, and that also is declared as no except. So if that move assignment operator does not throw, then we want to use a move. Okay, to use a move means this is simply just making a move ready. Remember that standard move function? Making a move ready. And so making a move ready means this becomes an R value reference. So if it becomes R value reference, then we know it's going to call the R value, the move assignment operator that will be used instead. instead of the copy. Now, if it doesn't have the move assignment operator that supports the no except, so it may throw as well. And then we may just do a copy. If this throws an exception, then we might as well do a copy, which is, you know, so it kind of just you're making a choice here. So you do the same thing. You say you want to move or copy the new one. Same thing with this function. And then see here you got this new array. Now, why is that important that you don't want to throw here? Because here's the thing: when you move, could it be dangerous? When you're moving, let's say you just kind of failed in the middle of this loop, and then you did a move, and then that move threw an exception. Now, what's going to happen? Because every element you have moved so far from the current existing elements member, they are no longer usable. So whenever you move an object, the old object is no longer usable most of the time. You're not supposed to. That's really what move means. It's not a copy. So then you're leaving the object, the current object you're operating on, you're leaving that in the inconsistent state. It's no longer usable. So that is not a good exception guarantee. So it's not exception safe. That's not a good idea. So you might as well say just use a copy, which is at least you're not going to damage your existing object if that throws. So that's why if your move assignment operator throws, it might as well do a copy. That's safer. Because a move operation is destructive. Now, so you have done that. Now, once you have this new array ready, right? So that's kind of the move and swap EDM. So you have a new array ready, and then you swap. So that's really, and then just also why the move operation needs to be no except. Okay, so that's the move and swap EDM. And then we mentioned there's this function that we're using, and how is this implemented? And we can take a look at how this might be implemented. Now, I'll just briefly mention this because maybe some people will get curious. So this is called template metaprogramming. Template metaprogramming is simply means it's a family of techniques to create new types and compute values at a compile time. Now, we're still dealing with the templates, of course, but we rely on the compile time evaluation. So this could be an implementation of this move assign if no except. Well, if you see, so first we look at the function body. It's very simple, right? We're just using the standard move to make it a move ready, so that returns a all value reference. Well, is it an all value reference though? Not necessarily, right? So is all value reference if, right? So there's a condition here. How do we enforce that condition? So we're using some standard utilities. These are in the type traits library, the type traits header. And so there's a lot of things defined over there in that header. And then that's the kind of primary utilities that we use for metaprogramming. Now, there's this conditional class that allows you to conditionally determine a type. So we're going to say, if this condition is true, and then the return type of this function, remember this whole block here is the return type, right? We're trying to figure out the return type. The return type would be a reference to const. If this condition is false, the return type will be a all value reference. Now, keep in mind that we can use the if there's a L value reference, right? Const is a const L value reference. Now we know and that can also be initialized with an R value reference. And well, this expression, by the way, it is a R value expression. That, okay, the type of this expression is the R value reference, but the value category of this, so that I did not mention this before, this is an R value expression. So that can be, used to initialize that return type if you want. Now, let's take a look at this condition. There's two clauses in this binary condition here. So the first one is saying, so using this standard function is no throw move assignable. You can look up into more details on the cppreference.com website. You can just look that up and it'll show you the details there. So this is actually saying if this type has a move assign, basically move assignment operator function that also is no except, or no throw, no except, the same thing. If it doesn't have that, this is saying if it doesn't have that, but it actually has a copy assignment operator, then we do the L value reference. Otherwise, we want to use the R value reference. Okay. So I don't want to dwell on this too much, but this is kind of maybe a little, and then there's one more thing I want to mention. There's a const expression that what this is meaning to say is this function can be evaluated at runtime. Compile time. That's kind of what this const expression means, is you're instructing the compiler to evaluate this expression at compile time. And the result of that can be used in the place where this function is called. So what that means is that will be the runtime. I mean, even though you have this function here, you almost have no cost of this is all evaluated at compile time. There's no runtime penalty, essentially. So now I've seen sort of two new members, the move members of a class. So adding that to what we already studied before, there's actually 6 member functions, and we call them special. And you got the default constructor, the destructor, copy constructor, move constructor, copy assignment, move assignment. These 6 special member functions, they're called special because under the right conditions, the compiler will generate them. And they're also the ones that you can, if you actually you declare your own, you can actually default your implementation by using equal to default, right? We have seen those before. You can also delete the generated ones by using equal delete. So these are the special member functions that, of course, you need to be aware. So there's actually rules about how to use them. Okay, in what situation the compiler is going to generate them or not generate them, right? So what's happening is if you actually declare any single one of the 5 special member functions, now the 5 means all those special functions except the default constructor. If you actually declare any single one of them, then the compiler will back off. It will not generate the other functions anymore. So that actually means you should normally declare all 5 of them together. If you're going to declare one and you declare all 5, that's called the rule of 5. There's also a rule of 0. What does that mean? Is try to use the default implementation as much as you can. Don't try to implement custom versions of those functions. How do you do that? Well, that means you should follow all those good, um, you should follow those rules that we have explained previously. For example, you want to use your smart pointers instead of raw pointers, use the right idiom, right techniques, um, to handle your resources so that they are properly reclaimed always. So if you do those things, then you don't have to implement special functions for those things. So then the default ones will just work fine. Let's summarize, and then we're going to actually take a look at a little bit of code. But so let's say a null value is an expression that typically results in a temporary value, and the L value is one that results in a more persistent value that address you can access. The move function from the standard library can be used to convert an L value into R value. I think we can rename this to call it move ready. It's really not doing the move action. The move action is done by the move constructor or move assignment operators. The moved object should not be used anymore. So keep that in mind. Once you move some object, the original should not be used anymore. If a function inherently copies one of these inputs, then you can just pass that by value. And so in that case, you don't need to have two versions, one that takes the L value reference, the other one takes the R value reference. Automatic variables and the function parameters, they should be returned by value. And remember, don't want to use that move function there because that's redundant. Secondly, when you do use that, you're preventing the compiler from optimizing it. Remember the copy elision. Now, the move member should normally be no except. We saw the move and the swap idiom, why that no except is important when you move members. And then the standard library containers, if you don't do that, the standard library containers, they will probably not even use them. They actually do a check, just like what we checked with that function in the meta programming. And it will see if it actually doesn't have a no except. It may just simply not even use them because it's not safe to use. So there's the rule of 5. You either declare all 5 special members, not the default constructor, or none of them. And then obviously the rule of 0 is even more important. Don't even declare them. If you try to use those smart pointers, the right techniques, and the standard containers, then you're fine. You should not need to worry about them. So let's actually look at some code real quick. So so the array class, the array class that we discussed before, this is actually the same example we carried on from the previous chapters. And essentially has a size member and they have elements a pointer that's kind of it holds on to this array. So let's take a look at for example, the move constructor. So you see the move constructor is actually a shallow copy. You would copy the size member and copy the member's pointer. That's really a move. The move semantic, typically you're doing a shallow copy. It's still a copy, it's just a shallow copy. And then once you've done that, a very important thing is that you need to set the old pointer to null so that when that is destructed, you're not going to cause um, an issue that, getting your new values reclaimed, because now you have essentially just copy the pointer. You did not copy the content, the object that's pointed to. So you do want to make sure you nullify the original. That's why the move operation is typically destructive. The object that you moved from should not be reused. And then we can take a look at actually the version that has all the members defined. Let's actually take a look at this guy. So this has the actually, let's take a look at the pushback. We actually saw this before in the slides. Okay, so that we already explained. And now the move and swap idiom is pretty much just the same as the copy swap idiom, except that here you use this move function to make the right-hand side operand move ready, so that the compiler will invoke when it says that this is constructing a new object from an all value reference, right? From all value, and so from all value, when you do this, this is gonna, well, this all value will be instructing the compiler to use the all value, the move constructor instead of the copy constructors. This is why this is a move operation. Okay. Now, if you don't use this move function here, this right-hand side, even though this is a parameter, you're declaring this as a all value reference. Now remember, the name of a variable, including the parameter, is a variable. This name is a all value expression. Sorry, is an L value expression. Okay, even the type. Now keep in mind the type and the value categories there are two distinct properties of expressions. Okay, so the RHS has a type of all value reference, but the RHS as an expression is an L value expression. So that's why you need this move function to cast that to convert it into a all value expression. This expression here with this function call with the move is a all value expression. Now, if you recall in the earlier example here, a function call, the all value expression whose return type is non-reference. Okay. Well, this example I actually did not list there's actually a whole very long list of all value expression. This is just some big examples. I did not list that here. In fact, this particular example is called one of the actually X value that we mentioned in the earlier. And this is an example of X value, but X value is an all value. So anyway, you just need to know that this is an all value expression. And so when it's an all value expression, the compiler is going to use the all value, the constructor that takes the all value reference, which is the move constructor. Okay, so that is worth explaining a little bit. That's why we also explain this move function. You're gonna see this used quite a bit with the places where you may want to, you're dealing with all value references. Then this is one of the things that you may use. So the rest is pretty much the same as before. So this is the new stuff, is about the move semantics, the move members of the class, and how the move members actually enable efficient copy operation. So instead of the deep copy, now we do shallow copy. So that's all I wanted to share. Thank you.